쪽에서 저는 커런트 미러가 아까 지금 WOL 레이셔가 1대1일 때 게이트를 조심하니까 GS가 같아서 커런트가 바뀌어야 된다고 생각했는데 이제 서브스레솔드에서는 VGS가 같아도 VDS에 따라서 리니어하게 변하잖아요. 근데 지금 저기 보면은 피모셀 쪽에서 드레인 볼티지가 다른데 커런트가 똑같이 바뀌어야 된다고 하시는 거잖아요.
Okay, let's record it, okay? Yeah, the question is, the current mirroring of a PMOS transistor. So this is I2, this is I out. So in the question is, in a subthreshold region, current has some VDS dependence. Okay, there is some constant times. Yeah, say, what's the effect of its drain source voltage in this current mirror ratio? We just assumed this is 1 because the gate source voltage are the same. But we are assuming my VDS is maybe around 3 VT, larger than 3 VT for saturation operation. Okay, we already assume that. So we assume all the transistors work in the saturation region in analog circuit, analog amplifier, right? Are the same. So this is a voltage headroom problem. We lose some maybe 3 VT here in the voltage headroom. Then this is only 1, right? This is 0, this is 1. No problem, right? In this current mirroring ratio. Okay, any other question? All right, let's continue. So our self-bias circuit is more intelligent. Let's just see. So it has a cascade structure there. Yeah. So our self-biased current source. Yeah, it's something like that. So I have a PMOS current mirror here. It is cascaded to increase the output resistance. And also, I have a MOS cascade current source there. Yeah. So, because I have a resistor there, I must have a diode on the opposite side, right? Yeah, I must have a diode on opposite side over here too. So I need a bias for this one. This one I need a DC bias, right? So for that purpose, see, for this one, for this bias, I have a small WOL transistor there. So the current must be supplied from there. So I have 2 PMOS transistors here. So it copied the current and then flow current through here, right? So this should be diode, right? It generates some voltage drop. Hopefully, yeah, 2 delta plus 1 VTH. Okay. Similarly, I need a PMOS diode here to supply current here, to supply DC voltage drop here. So I need to get copy of that current from MOS cascade transistors. Oops, this should go there. Yeah, so this one has two operating points. One is zero current. The other is the desired non-zero current. So to avoid that zero current, we need a startup circuitry. Startup circuitry. See, then that startup circuitry has, how does it look like? Yeah, my startup circuitry has some, let's just see. Oh, small MOS transistors there, to flow current there. So I have a oh no, I think this is something like that. Yeah, this used to be my startup circuitry. In the previous version, we use inverter, right? Inverter. Say for the zero current state. Yeah, this is almost zero, and this is almost VDD. Then no current flows, right? Zero current flows. This is a stable state. Yeah, to get out of this, we need say for this one, see, for this is zero, this is very high, almost VDD, so it starts to flow current, and then once the current start to flow, this zero current state goes to the non-zero current state, okay? Because of positive feedback. Yeah, in your homework, you use the inverter here, right? Instead of grounding. Sometimes it may be, it has, it's like inverter loop, because this PMOS common source transistor is another inverter, okay? This is a kind of inverter loop, but there is some memory there, okay? So some people don't like this loop, okay? Yeah, actually, so I want to suggest just use this one. This should be large W of L. This should be very small W of L. This is because, see, once it goes into desired operating point, so I must turn off those transistors, then this startup circuitry is isolated from the main current source. Okay? Yeah, then this should be very small. Otherwise, if this is very large and it still flows current, some current, then startup circuitry is not isolated. Okay, so here, see, at the non-zero state, this has some significant voltage applied at this node, right? Then it starts the current. This is still on because this is grounded. The gate is grounded. So, this voltage is determined by W ratio of this MOS transistor and this PMOS transistors, right? So if this is very large, this voltage is almost zero, and it completely turns off those two transistors. Okay? So I want to suggest you eliminate this inverter, CMOS inverter. No inverter, just grounded. Use a large difference in W ratio of this MOS and PMOS. Okay? Yeah, let's simulate try to simulate this one. Too much. Oh, where am I? Oh. Okay, it's too much, too much content. Okay, let's eliminate the startup circuit here. Still large. How come? Oh yeah, now okay. 10, 1 by 2, 20 by 1, 1 by 2. Okay. Where am I? All gone? Uh-oh. Oh yeah, here. I am, oops. Huh. I want to eliminate this part. Okay, where am I? Oh yeah, now here. Okay, this is a startup circuit part. Uh-oh, too much. Okay, so here's the, this is the main self-bias circuit. So we have 10 by 0.7 for MMOS, and one, the diode is 1 by 2, PMOS all 10 by 7, 20 by 7, and 1 by 2, okay? So in the previous circuit, see, this one is all 10 by 0.7, this is 1 by 2, this is 20 by 0.7, this is 1 by 2, and what else? Let's see, how about that size? That size is 40, right? 40. This is 40, right? This is 360K. So in the previous case, this is 40.7, this is 360K, okay? All others are the same. So I use the small transistor to guarantee enough voltage drop to operate those transistors in saturation, okay? So you need to adjust this W of L size to get some voltage headroom, okay?
질문. 근데 여기서 인버터 쪽에 저쪽 그 부분에 생기는 스테빌리티 그게 아니면 얘는 그 사이즈에 상관없이 그래도 L분의 W에 해가지고 만약에 VDD 값이 높다고 하면 항상 흐르는 그 커런트가 있잖아요. 얘가 평균이 되면.
You mean the leakage current
예.
of self-bias circuit?
만약에 VGS 이게 VDD가 좀 크다고 하면 얘는 그게 되게 좀 크게 작용하는데 얘 같은 경우에 근데 여기 있는 그 루프의 개인이 1보다 작으면 이거 자체는 항상 얘는 꺼지니까 사이즈를 그렇게 하고 여기도 작게 하고 크게 하면 그렇게는 그게 더 안 좋고.
So I think your question is related between, I mean, some interrelation between startup circuit and then this current source circuit. Is it right? Some interaction. But that's no good. So we want to isolate those two parts. Once it goes into the proper operating point, non-zero operating point. We want to completely isolate the effect of a startup circuit from the current source circuit. Okay, so yeah, that can be performed by turning off those two transistors, right? If I make this voltage very small, like 0.1 volt or less than that, so it is turned off. They are turned off, right? So it is isolated. But there are still some leakage current here. Yeah, in this example, this may be around 1 microamp or larger. This is, say, for example, 0.1 microamp, 100 nanoamp each, four branches, right? So it has only 0.4 microamp in the current source. It has larger than 1 microamp in the leakage path. That's a problem. Yeah, to avoid that, I need to have a huge, very large WL for this NMOS. Very small WL for this PMOS. Then I can reduce that leakage current part, right? Yeah. Looks like that's the only. Yeah, if you can use inverter, you can make this zero leakage current. Inverter, but inverter is sometimes dangerous because of memory operation there. They are cross-coupled inverters there. People don't use it. Okay, so let's just see. Yeah, so you can see this current. My current is around R MVT log 4, right? Because this W-level ratio is only 4. So I don't know exactly, and maybe 1.1, VT 25 millivolt. What's log 4? Is it 1.5 or maybe, I'm not sure, log 4. 360K, what's this thing? 1.5, 30. Yeah, maybe around 100 nanoamp, I'm not sure. Around, it goes around that value. Okay, so let's simulate this circuit. Where is my Sigma Spice? Oh yeah, here. Okay, so simulate. How come it takes time? Let's just see, graph. Chapter 3, we did. Or let's just say, this current, see, this is transient. No, DC. Yeah. This is current through resistor, 106K resistor. It's around, you can see, can you find it? It's around 100 nanoamp. How about the leakage current? Wow, leakage current is huge. At the 3.3 volt, the leakage current is around 700 nanoamp, right? It's very large. Oh, let's look at that part, that startup circuitry part. Where is my startup circuitry? How come it looks like strange here? Oh yeah, fine. Yeah, I made a startup circuitry like that. Where is? Oh, this is that small transistor, two small transistors. What's this thing? NX. Yeah, this is NMOS. Where is my PMOS? Ooh, my PMOS is huge. I can adjust those two. Okay, they are commented out. So sometimes, if you have some stability problem, like those current waveform, you can put some capacitor. Let's just see. Yeah, 21 by 0.35. Huh? Yeah. Yeah, for the startup circuitry, I used this is 1 by 0.35 minimum size device, right? And then what else? This is 0.7 by 100, right? I made a huge to reduce leakage. This is 20 by 3.35, right? So this voltage should be very small. This is NX, right? What's the NX voltage there? Let's see. What's the NX voltage? No. Oh, yeah. It's gone. Okay. Let's look at the transient. What's the NX voltage? My NX voltage become very small. Okay, let's look at the. This is NX voltage after startup. Let's see. What's the value? My NX voltage is 2.9 millivolt. It's almost zero, 2.9, 3 millivolt, right? 3 millivolt. Because of PMOS is very small. How about the current? So this is, oops, actually I have to eliminate that part. Let's see, okay. Leakage current. All right. So this is my current through resistor, I think. Say, what's the current through resistor? Yeah, around 99 nanoamp. How about the leakage current? Leakage current is 657 nanoamp. Huge, right? Still huge. Much larger than that. And then what else? Let's see. My NG1, NG2, okay, something like that. This is a bias voltage. The gate bias voltage. Gate bias voltage went to NG1 is a lower side gate bias voltage, which is 0.5 volt. How about NG2? NG2 is a 0.624 volt. Okay.